Okay, let's take a look at abstract relationships. This is definitely some new thinking, but once you get a hang of it, it's really not that bad. So I'm going to ask you really how one variable affects another variable. And typically we're going to like double or triple one variable. So let's just go with some easy ones right away. So let's say I have the situation where I'm dropping something. Okay, so I go up to a certain height and I drop it, and it takes t seconds to fall. Well, what happens if I go up to 2h? What happens to the new t? And the question then is, what I'm asking is, if I double this variable and I keep gravity, of course, the same, what happens to this variable? And it will turn out that the height and time are not a linear relationship. Doubling the height doesn't double the time. It's not h and t, it's h and t squared. You also can make a conceptual view that if I take an object and I drop it and it goes da 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 and it takes t seconds, well, how long would it take that same object to fall that distance? Well, t seconds. But then how long will it take to fall this? Well, that part, we'll call that t2, certainly is less than t1, where t1 in here and t1 there are the same. It's already moving fast here, and so the average velocity over that moment definitely is less, or definitely is greater than the velocity here, such that it's going to travel that distance in a shorter amount of time. So we know that this whole thing is actually less than double. Of course it is. They're not linear related. Doubling the height does not double the time required because the whole thing is accelerating. If you were traveling at a very constant velocity, right? If you were doing a very boring question, x equals vt, you're in a car. Of course, in that case, if you double the distance required to travel and you keep the velocity the same, then it takes double the time. If you say, how long does it take to go 10 miles? How long does it take to go 20 miles? Of course, doubling the time. Doubling the distance doubles the time if you're not accelerating. But we're accelerating here, so that this velocity is going to be greater than this velocity. And so the question is, how much bigger is it? If doubling the height doesn't actually double the time, what does it do to it? And it turns out that if you want to put a 2 on this side of the equation, mathematically, what would you do over here? And if you increase that by the factor of square root of 2 squared, it's going to create a factor of 2. Now these equations are balanced again. If you increase t by the square root of 2, that factor gets squared. The square root of 2 squared is 2. Increasing this by the square root of 2, which is like 1.41, will increase the height by 2. Okay? So if I double the height, I increase the time it was in the air by the square root of 2. Over here, I double the distance, I will in fact double the time. Or you could say it in reverse. If I triple the time driving, I'm going to triple the distance. So we're looking at all these different relationships on how this works. And again, if you want to, feel free to actually go through a numerical example of this, okay? So what you could do is you could find the height. Let's say the height is 20 meters, right? And we did 1/2 gt squared. We said, okay, 20 equals 1/2. I'm going to use 10 because then I can do it in my head. So this is 20 equals 5 t squared divided by 5 is 4, taking the square root is 2. Okay, so I just proved to you that if I drop it from 20 meters, it's going to take 2 seconds. Okay, so let's double that to 40 meters. So now it's 40 equals 1/2 gt squared. So then it's 8 t squared, and then t is the square root of 8, which is 2 radical 2. And now numerically, I've shown you that doubling the height does not double the time, of course not. it makes it the square root of 2 times bigger, is what we said. Again, this is a quadratic relationship. Doubling h, you don't have to increase t by that much because that gets squared. Over here, you know, if I'm driving 10 meters per second and I do it for 5 seconds, of course I go a distance of 50 meters. If I continue to drive 10 meters per second, but now I double the time and I go for 10 seconds, well then of course I go for 100 meters. Right? Of course, doubling the time doubles the distance in this scenario because that's how x and t are related. Okay, let's do a different one. What about the v squared equation? It's probably one of my favorite ones because there's a square relationship again. Okay, so let's say I want to stop and I don't want to hit something. So this is, I'm driving a car and I'm going this way at some v naught, and there's a certain distance, and then I need to stop here, okay? So then my v final is 0, and this is some distance x, and I'm going to accelerate at some value a. It doesn't really matter what the acceleration rate is. So let's say I want to stop, and I'm going to go, let's go 20 meters per second. I'm going to stop, so it's going to be a minus sign, and that's going to be 400. So let's make this something I can do in my head. Let's make the acceleration rate is 2, and that doesn't change in this scenario, right? That's held constant. So if I'm going 20 meters per second and I'm going to stop at 2 meters per second squared, that's my acceleration rate, you know, what's the distance required? So this is 0 equals 400 minus 4x, and so then the distance then is 100 meters. So far, so good? Okay, so then the real question is, what happens if I drive twice as fast? How will that be affected? So what I'm asking you is, how is v naught related to x? If I double v naught, what will happen to x? Now think about that for a second. Here, doubling h made t go up by the square root of 2. Here, doubling t made x go up by double. This is a linear relationship. Well, this will end up being the exact opposite of this. Here, I double the linear variable and I want to know what happened to the quadratic. Here, I'm actually doubling the quadratic and I'm saying what's going to happen a little at x. Again, this isn't changing, a isn't changing, of course 2 isn't changing because it's a constant. But if I double this quantity v naught, I then end up squaring it. Doubling 2 ends up squaring it and making a 4. I'm going to claim that x goes up by 4 times the amount. And I can show it to you just using numbers, right? I still want to stop. I'm going to double that, make my initial velocity double, keep acceleration rate the same. This is 0 equals now 1600 minus 4x, and I get x equals 400. Look what happened there. If I doubled my initial speed, I quadrupled the distance required to stop. Because of this is, I'm doubling the squared quantity, and I'm seeing what happened to this quantity. You know, everything just got reversed from these guys. Okay? And I can do any equation I want. I can look at the period for a pendulum, something we might look at. And let's just tell you, it doesn't even matter, you don't even need to know what that is. But let's say t is the period, meaning the time it takes for this pendulum. Right, there's your pendulum. And your pendulum is swinging back and forth. Wom, 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 wom. And I want to know, how does the time it takes to go get affected by the length of the pendulum? And this is just little g, so this is the gravitational constant on Earth, right? This is 9.8. That's not going to change. So if I want to triple the period, so I have a certain pendulum of length L, and it's got a certain period of t. But what I want is I want to design a pendulum. Clearly it's going to have to be longer, but I want that one to have 3 times the period. What's the new length? So what do I have to do to this variable to triple that variable? Okay? Okay, now let's look. How is L related to T? It's the square root of L is equal to T, or proportional to T, excuse me. And so what do you have to do to L to make this go up by 3 times? You're going to have a 9 there. 9 times the length. Whatever this length is, you have to make it 9 times as long in order to triple the period. Think about the relationship. If I multiply this by 9, I'm going to end up taking the square root of it. The square root of 9 is 3. Multiplying this guy by 9 really only changes that equation by a factor of 3, which means this would be tripled. Now, this example numerically is going to get really messy. First of all, there's a square root in there and there's a pi, but you can go ahead and do it if you want. Go ahead and use 9.8 for g if you wanted to. Pick some length, pick 5 meters, and then pick a new length of 45 meters, right? And I guarantee that this period is a certain value, and this period is going to be 3 times whatever that number is. So this number is like, let's say, question mark. That's for sure going to be 3 question mark. Okay, 9 times, triple. Doubling this quadruples that. Doubling the time, of course, doubles the distance in that scenario. Doubling the height only makes that go up by the square root of 2. You really have to think about how the variables are related, and that's what we do all the time in physics. We want to know the relationship between variables. How does messing with one variable affect the other variable? And these are probably the 3 classic cases. There's a quadratic and there's a quadratic. In this scenario, I messed with the quadratic variable, which gets squared, which increases the growth factor. Here is quadratic, but I messed with the linear variable, and the quadratic variable doesn't get affected enough. Again, of course, increasing height increases time, but it's not double-double. Here, since you're moving at a constant speed, I just moved at a constant speed for double the time, and of course I went and then double the distance. This is double-double. And there are things like that, right? That's a linear relationship between the variables. I could ask that over here. I could use the v squared equation. And in this scenario, let's say I'm braking. So I'm just going to go ahead and put a minus sign there. Let's say now I want to know how is the acceleration rate related to the distance. So I'm not going to mess with this guy, and I'm not going to mess with this guy. How are those related? Well, look at them. They're linear related. So if I increase the acceleration by a factor of, let's say, 5, what happens to the stopping distance? Well, we've got to remember here, they're a product, right? This is like saying, let's say I'm going the same scenario. So I still want to stop. I'm still going 20 to ax, which really means it's like 400 equals 2ax. Do you see how they're inversely related? If I increase the acceleration by a factor of 5, then I decrease the distance by a factor of 5, which makes sense. If I make my brakes 5 times as good, I'm going to be able to stop 5 times shorter distance, right? That goes up by a factor of 5, that goes down by a factor of 5. A and x are linear related. They're not these square guys. And again, so it's not like everything in a v squared equation has a quadratic relationship. It's just v and a and v and x do. But a and x, they're the same. They're both linear things. So, and in this case, all of these were increased, right? Increasing height increases time. Increasing time increases distance traveled. Increasing my initial velocity increased my stopping distance. Increasing the length of the pendulum increased the time it takes to swing back and forth. But in this case, I picked 2 variables that had an inverse relationship. Increasing the acceleration, increasing the braking power, decreases the stopping distance. Okay? Hopefully this gets you started. I know this is complicated, but after you do a bunch of these, and the AP loves these questions, you really get a hang of them, and you'll be able to just look at the equation and tell me what happens if I double or triple something.